Hello, Stat 200, and welcome to Lesson 4. This week, you're going to be learning about probability distributions. We'll learn about probability distributions for discrete random variables, binomial random variables, and continuous random variables. Let's begin by reviewing what a random variable is. This is the definition from your textbook. A random variable denotes a numeric quantity that changes from trial to trial in a random process. In other words, it's something that varies randomly. These are the key topics that we're going to see this week. Let's start by looking at discrete random variables. Recall from earlier lessons that a discrete variable is a variable that has a limited number of possible values. Here's one example. This was taken from the Stat 500 online notes. Let X equal the number of prior convictions for prisoners at a state prison at which there are 500 prisoners. The table we have here is known as a probability distribution table. To read this, if we look at this column, we can see that the proportion in this sample that had 0 convictions is 0.16. In other words, 16% of individuals in this sample had 0 convictions. We could write this as P of X equals 0 equals 0.16. In the next column, we see that the proportion of individuals in this sample that had 1 prior conviction is 0.53, or 53%. We could write this as P of X equals 1 equals 0.53. We could also use this table to find the proportion that had a certain range of prior convictions. For example, the proportion that had X less than 2 or fewer than 2 convictions is equal to the proportion that had 0 plus the proportion that had 1. This equals 0.16 plus 0.53, which is 0.69. So we could say that 69% of individuals in this sample had fewer than 2 prior convictions. This is as far as we're going to go with discrete random variables in this course. Looking at this chart, we see that we can have discrete or continuous random variables. One specific type of discrete random variable is the binomial random variable. We're going to look at this next. For a variable to be a binomial random variable, all the following conditions must be met. There must be a fixed number of trials. In other words, there must be a fixed sample size. The probability of a success is the same on each trial. And finally, the trials are independent of one another. There are a few examples of binomial random variables in your notes this week. In terms of the notation that we're going to be using, n equals the number of trials. The number of trials must be the same for every experiment. P equals the probability event of interest occurs on any one trial. This probability must be the same across all trials. Let's look at how we can compute the probability of a certain number of successes given that we have a binomial random variable. This is the formula from your online notes. It's also in the textbook. This is what we use to compute the probability of k successes in n trials. Here's one example. In American roulette, if you bet on red, the probability of winning is 18 over 38, or 0.474. If you play 4 games and bet on red each time, what is the probability that you will win exactly 3 games? In this case, n equals 4 because there are a total of 4 trials. K equals 3 because we want to know the probability of having 3 successes. And P equals 0.474. We can plug these values into the formula. If you need a review of combinations and factorials, in your online notes, you'll find a link back to lesson 0. Working through this equation, we find that the probability that x equals 3, in this case, is 0.224. In other words, if you play 4 games of American roulette, betting on red each time, there's a 22.4% chance that you'll win exactly 3 games. When you're computing the probability of a single event occurring, so here probability of x equals 3, it's relatively simple to do this by hand. I'm going to go to Minitab Express right now, and I'll run through this one really quickly there, but we'll see where Minitab Express really comes in handy is when you want to find the probability of a range of possible number successes. So in Minitab Express, we'll work with a blank data set. We'll go to Statistics, Probability Distributions, Distribution Plot. We want to display a probability. The default is a normal distribution, which we're going to see at the end of this lesson. Here we're working with a binomial distribution. There were 4 trials, and the probability of a success on any one trial was 0.474. We have a specific x value. In the example that we just ran through by hand, we were looking for the probability that x equals 3. To do this, I'm going to select middle, and I'm going to find the probability of being between 3 and 3. This will give me a distribution plot with 3 shaded in. We can see here the probability of winning exactly 3 out of 4 rounds is 0.224068, which is the same probability that we got using the formula and doing the hand calculations. What if we wanted to know the probability of winning 3 or more games? Because in order to make money, you would have to win more than half of your games. We can construct another probability distribution plot. Again, a binomial distribution. There are 4 trials with a probability of success on any one trial of 0.474. This time I want to know the probability of 3 or more wins, so it's a right-tailed distribution plot. I want to shade in the value to the right of 3. Now we can see both 3 and 4 are shaded in this plot. The probability of winning 3 or more games is 0.274548. Another nice thing is that when we hover over one of these bars, we can see that the probability that x equals 3 is 0.224068. Down here, the probability that x equals 4 is 0.050479. Your online notes this week include a few examples of constructing these distribution plots in Minitab Express. It includes instructions and videos using both the Mac version, which you see me using here, and the PC version. Next, let's move on to computing the mean and standard deviation for a binomial random variable. These are the formulas that you're going to see in your notes. Unfortunately, this is not something that Minitab Express will compute for you. You will have to use these formulas and do the calculations out by hand, but they're fairly simple. For the mean of a binomial random variable, also known as the expected value, or E of x, is equal to n times p. So in this particular example, 4 times 18 over 38, or 0.474, which equals 1.895. So to interpret this value, I would say if you're playing 4 games and you bet on red each time, I would expect that you would win around 1.895 games. Or over a large number of experiments, so if we would repeatedly play 4 games, count how many times we won, play another 4 games, count how times we won. If we would take the mean of all of those, that mean would be 1.895. That distribution would also have a standard deviation of sigma, which is the square root of n times p times 1 minus p. Plugging our values from this scenario into that formula, that equals 0.999. So again, if we were to repeatedly play 4 games and record how many times we won and plot out that distribution, it would have a mean of 1.895 and a standard deviation of 0.999. Now, We'll move on to continuous random variables. This is the last type of random variable that you're going to see this week. In this lesson, we're going to work exclusively with normal distributions. These are bell-shaped distributions, such as the one shown in this plot here. Later in the course, you'll see other continuous distributions. I believe next week you'll see t-distributions. When we do regression, you'll see the f distribution. And when we work with two categorical variables in lesson 11, you'll see the chi-square distribution. What we see in this plot here, though, is one special type of normal distribution. This is the standard normal distribution. It's a normal distribution with a mean of 0 and a standard deviation of 1. The notation that your textbook uses is n, and then in parentheses 0, 1, meaning the n stands for normal, 0 is the mean, and then 1 is the standard deviation. This is also known as the z-distribution, which you learned about earlier in the course. If you've taken a statistics course in the past, you may recall having to read a z-table. It was probably a few pages long, tons of numbers on it. We are not going to be doing that in this course. Instead, we're going to be using Minitab Express. Just as we use Minitab Express to construct a binomial distribution plot, we can do the same thing with a normal distribution. Before we go over to Minitab Express, I want to remind you of the empirical rule. So recall from earlier lessons that according to the empirical rule, given that a distribution is normal or approximately normal, we expect about 68% of observations to fall within one standard deviation of the mean, 95% of observations to fall within two standard deviations of the mean, and 99.7% of observations to fall within 3 standard deviations of the mean. I'm going to hop over to Minitab Express now, and I can show you how these values can map on to the standard normal distribution. So recall from earlier that a z-score is a measure of how far an observation is from the mean in standard deviation units. So we're going to make a probability distribution plot here for a standard normal distribution, which is the default in Minitab Express. It's a normal distribution, mean of 0, standard deviation of 1. We have specified x values, or in this case, they're also z-scores. And we want to find the middle. Let's find the middle between a z-score of -1 and +1. Right? According to the empirical rule, 68% of observations should fall within one standard deviation of the mean. So those would be between z-scores of -1 and +1. We can see here, recall the empirical rule is really just an approximation. The exact proportion of scores between -1 and +1 is 0.682689, approximately 68%. We can do the same thing for 2 standard deviations, which is actually what your textbook uses most frequently. That would be between approximately 2 standard deviations of the mean, so z-scores of -2 and +2. Right? So 0.954500, or approximately 95%, fall within 2 standard deviations of the mean. So this is how you can use Minitab Express to construct a distribution plot to kind of show where those empirical rule values are coming from. There are a lot of examples of this in your online notes this week. This is something that you should become very familiar with because we are going to be constructing distribution plots in many of the remaining lessons. This concludes the Lesson 4 overview video called "These are the key topics that you're going to be reading about this week." As always, if you have any questions as you're working through the online notes, the textbook, or any of the homework assignments, please post them to the Lesson 4 discussion board on Canvas.